Okay, I'm gonna just do it without the PowerPoint. First, I like to resolve the question we had last Wednesday. So it's my mistake because all the equation we developed in page 14 and input and output noise are included. So if you look at the page 17, about near the bottom, there is not the definition. We derive this equation set, but right now I wrote there as a GYY and a GXX. You remember just the equation near the bottom? And this is really wrong. I tried to derive it, didn't work. Of course, naturally, that's wrong, so you can't derive the wrong answer. So here, the right one is GVV and GU is right. This is on page. This is in page 14. So this last page is kind of the summary. So if you take a look at the page 14, page 14, and this is the equation set. Page 14 or page 15, I'm sorry. Page 15. That confuses. I spot that here. Page 15. The H, what is H here? Page 14. Okay, 13. Page 14. Actually, not page 13. I couldn't locate. Where is that equation set? Same equation set. This is right. This page 14 at the top. Oh, it's here. 누가 이거 했냐? 잠깐 보자. 이거 page 16. Okay, page 14. Right here. The GVV over GUU is H absolute square. Right? That's what the equation said. And if you go into page 17, that's identical equations, okay? So what I did in 17, page 17 is a summary. Then you have to be really careful because depend on the diagram, it related to the equation set. So just to put the equation set is really dangerous. That you have to be careful. I just happened to put that in, and that relate to the case on page 14, okay? So shouldn't be confused. But this in page 17 should be this. It's in page 14, okay? So we're gonna, I think so far, I spent a lot of time to explain how to derive the necessary H or GYY, whole bunch of different things, GUU, GVV, but all the notation is very consistent. V is output side. U, I always use input side. X is always input, and Y is always output. And for the noise, M is always input noise. And N is always output noise. Very consistent. And this chapter 4, the part B, is something like a 30 page. But if you look at carefully, the flow is pretty similar to what we have done in chapter 4. So then after I finished chapter 4b, I briefly talk about the beginning of the chapter 5 and going into the experiment. That experiment, we're going to do that starting today by a video clip, looking at video clip. Then also Monday and Wednesday, I'm going to really spend only twice. Then you can go down to the basement. Then I'll be down there Monday. Then I'll explain overall pictures. Then I ask Higyu spend some time to practice the DSA, to operate and all that. Then I want you to go through all the work, experiment I call 1 and 2, which I'm going to give you Monday morning, the experiment number 1 sheet, then experiment number 2 sheet. Then you can, but we cannot print because that machine is old machine. But as I mentioned to you, we save a lot of money. All the functions are working. Everything is working. Brand new cost $25,000 around the mid 1900. So around the 1995, or I think 1990, I bought that machine, 5 of them. So that cost quite a bit, but now they have a better machine, but better machine doesn't work. We have used the machine, but doesn't work as I really want all the options. So that's what we're going to use that. So we can print it. That's the problem, because we use HP IV plotter. But nowadays, you don't use a plotter. So that's a decade ago. A plotter is, I really enjoyed to use a plotter in the school environment. Doesn't matter whether it's a HP fancy printer or plotter. But we don't have a plotter. So if you locate some used plotter, of course, I'm going to bring in. So this lab, this semester, but I feel you are still lucky that you can really manipulate the DSN to achieve what you want to see, okay? All the correlation function, autocorrelation function you can generate, and the cross-correlation function, all the spectral function you can really get it what you want. If you don't get it, then your answer is wrong. And then the approach you really get it is wrong. Gamma XY square, you will get it, and all that. Phase and magnitude for frequency response function, you should get it, okay? So anyway, next Monday, we'll assemble here. I'll give a talk for about 10 minutes to explain what lab we're going to do. Then we'll go down there. And Wednesday, same thing. We'll be here for 10 minutes, then we'll go down there. So at least 2 hours. Any other time you can talk to Higyu. Then we'll open, of course, the lab door. Then you can all come down and do whatever you like to do. So in that sense, far better than last year. Last year wasn't able to do because until about 3 weeks ago, I didn't know what to do about the lab. So that's why I didn't bother to put the lab time in the course assignment. But that's what we're gonna do, okay? And this is 25 minutes after. And chapter 4, part B, this is a really old version, but you have a new version. I'll put the new version in. And I want you to read ahead of time. You may find some mistake, as you found the one last Wednesday. Then I want you to point out in the class that we can correct it and all that. So this is the section, the noise pass through the system. This is new situations, okay? So far, noise was independent noise, didn't go through the system. So this is the case, noise passes through the system. Another case, this is what we have done it already. So this is noise does not pass through the system. So this is kind of the similar situation. Then the parameter to find is different. The other, the chapter 4, let's say A, we were talking about getting into GUU, GYY, all that. But here, I concentrate on the H functions here. H expression as a function of noise in there, okay? So I want you to read as much as you can, so then I can just move a little bit faster, because you read already. Then some good implications I can discuss, rather than this 1 + 1 is 2, not 3, I can just step through quickly. Then getting into a little bit more lab. That's my intentions, okay? Okay, so you will see about 30 minutes the video clip on the mostly lab 1. And this is a homemade video clip. It's not a professional. All I did was myself and the lab manager and technicians. We just get into the lab and we video the tape. Okay, so it's just not professional, the video clip, but it is good. But myself look like from Africa, but as you know, I'm not from Africa, so it's all good. Okay. The random vibration and spectral analysis. This is the first lab. We have 3 labs. I'm broadcasting this to Washington, D.C. that time. And this is really in-house videotaping. We have 2 gentlemen here. They are really talking to my face looks much younger. He's our the lab manager, and he's in charge of all the lab. So he is going to help this videotaping throughout the course. And next, Tom Christian is my boss in fact. This is informal. He's a fantastic guy. Knows hardware, software, all the lab equipment. He's a perfect person. This is non-professional, in-house kind of work that we are working on. Okay, and what we're going to do in the first experiment. So first experiment, I put it down. You're going to do this, okay? Here. We are going to measure the autocorrelation function. So it's zooming in. This autocorrelation function, as you learn, which is R xx tau, is mean of the xt multiplied by xt plus tau. We are going to give you from the measurement of this quantity. And here, for example, this is a sine function. If you measure the autocorrelation of the sine function, then you will, simply speaking, when you take an autocorrelation of a harmonic function, it's back to the harmonic function. And you will see that here, I think you computed, or you will compute the autocorrelation function of sine wave, which end up to have x squared over 2 cosine 2 pi f naught t. So here f naught t is, of course, a tonal frequency. And next we are going to measure the cross correlation function of two functions. Here, the x and y function. And time delay is, as you know, the tau here. So this is cross correlation function r, x, y. And next we are going to show you the measurement of probability density function and cumulative distribution function, and we'll give you the PDF function, PDF for sine wave with the Gaussian random noise. So as we learned in the class, this is a probability density function for sine wave, and this is a Gaussian random noise. In other words, this is the Gaussian the density function for random noise. Okay? Then when you add these two together, you will have such a shape, which is really I call the sine wave with the Gaussian noise. So here, this is a probability density function for the combined wave. Okay, so that's what we're going to measure. So the waveforms we are going to deal with is a pure sine wave, and the triangular wave, and the square wave, and pure random wave, which is really pure random noise, you could say that. And last waveform is a sine wave combined with the Gaussian random noise. Again, the Gaussian random noise means it's really random noise with the Gaussian distribution, Gaussian probability the density functions in, like as I showed here. In chapter 2, of course, we covered all the basics of probability functions. Okay, so we are going to show you the experimental equipments right here. This is a very simple setup. I'm going to explain all this instrument, what those equipment does. Here, the top one, this is HP, the wave generator. It's a function generator. It can generate this harmonic function. It can generate, as you said, the middle button. This is the first button is a rectangular wave, and the second is a triangular wave, and third here is a harmonic wave, simply speaking sine wave. So this is a function generator, number one. And we have another function generator. It has the same thing, but this is made by WaveTech. But it looks different. This is HP, this is WaveTech. Both serve as same instrument. This is really nothing but the function generator. And we can set the frequency in the all different range. So right now, I set up the frequency for both in 10 hertz, pretty low frequency. It can go way up, okay? And this is a mixer of the two waves that we put that in here. And this particular one, this is a particular one goes to channel A. if you look at here, there is A, channel A, and this goes into channel B, and this I call the box B, and this is the box A. So by turning this particular knob, I can put the box A in display and box B in display. But as you see here, this is the oscilloscope. The top line is always box A. In other words, as you see here, this the cable goes to the A. A is shown at the top. You may not see that. This goes to A, and here it goes down to this. This is A channel, channel A. Channel A is right here, and this channel A goes to so-called the DSA box. This is a digital signal analyzer on channel 1, okay? So channel 1 takes up the signal from the function generator, the box A. So A is always playing right here at the top, okay? This is right now, just the two channels are here. Top is always channel A, the signal coming from the box A. This box B, well, sorry, this the lower signal is coming from here. So this is a channel 2. If we look at carefully, it said output right here. So this is second channel right here. This is the second signal, lower signal, is based on whatever I turn here. Right now, this is, I point to this in A, which means output for this is the channel A output, which is identical to this. So now, if I put it, set the function B here, so now this is the output, of course, as you see here. This is the B, which is a lower the signal, which is really right now is a B here, which means this is the signal coming from the box B. So if I change this from the sign to the triangular the wave, as you see, this is output. Output is set to B and from the box B. So this is a triangular pulse. So I'm going to move back switch back to B. Then as I did, I happened to touch this knob frequency dial. So back to the 10 Hertz. Okay, so this channel B, which is output is from here, and this output is based on this knob here, okay? And another thing I can maybe just demonstrate is, I'm going to turn this to the triangular, the wave function, triangular. So now it's this is a pointing B, which means that this is output. Then if I change the knob to here, which is A plus B. So this is A plus B is output, okay, which displays here, which means, which is really combination of this, the harmonic function combined with the triangular, the functions. So display, if I change the knob to the third location, A plus B, then it shows that this particular lower signal is combination of harmonic plus the triangular, the wave function. So turning back this to the sign, turning back to, I'm sorry, this is to B here. So now this is, I changed this knob to sine, harmonic function, and this I changed to B right there. As you notice that the top signature, which is coming from box A, is steady, is kind of fixed. And the lower signature is flickering. So this is really, simply speaking, the phases keep changing. Because a wave is passing, then it just takes a segment, takes the window, the signal, window of the signal. So that's what's happening here. So what we're going to do, when we're going to add this flickering part into the fixed part, okay? So phasing is random. So here is phasing is random. So when you impose it all together, then the time delay will be automatically incorporated into the system. So I'm going to now, these two wires going down here to a digital signal analyzer. This is really fantastic box. We bought this about 6-7 years ago. That time, this box was fantastic. This was something like we paid $25,000 per box. We bought like 4, okay? And this is a 2-channel digital signal analyzer. Each channel can accommodate 100,000 hertz. In other words, 100 kilohertz. So each channel. And nowadays, they don't sell this kind of the box any longer. Everything is all goes into the notebook, okay? And they program right in the chip. Sometimes they programmed in. So, but still, this is I call the Cadillac. It's a beautiful machine. It's a 2-channel digital signal analyzer, and you can measure the. Today we're gonna just do, as I mentioned, we're gonna really measure the autocorrelation function, cross-correlation function, and also the probability density function for different wave. This does them all. Okay. Of course, in addition, this does way more than what we cover even in this course. So, okay, we'll take just a break for a minute, okay? Then we'll come back. Give you a demo. First, I'm going to show you the autocorrelation function measurement, which is RXX. So I'm going to use only the top signal, which is coming from the box A. This happened to be the sine wave. So when you take a autocorrelation function, then of this harmonic function, the resultant gonna be the if this is sine, then you can say cosine. That's what we know. So as I did already here, I did already autocorrelation function, then I'm going to take a measurement. So I'm going to push the start button. I didn't really explain what this does. This set up the type of the measurement. So right now, this measurement is for channel 1. Channel 1 is the signature coming out of this box A. So as you see here, this is autocorrelation function for the sine wave. See, this is, I'm taking average exponentially. It keep taking the signature, then it keep averaging. So now it's 10, 11, 12, 13, averaging 14. So this becomes quite stable. Now it's pretty stable after 16 average, okay? Of course, we can communicate together when I give you a demo, but after I show you this in the class, then we'll have a discussion sessions on that. And now I'm going to change the wave. This is a sine wave. I'm going to change the signature of the box A to square wave. So as you see, this is a square wave or rectangular wave. So this is coming, so this is plateau coming down and up and down. So this is the square wave. And when you take a autocorrelation function or take a measurement, you see here, this is a triangular wave. Eventually, I'm recording today. Today happened to be 26th of October. You haven't learned probability or such a function, but I think I'm going to assign this as homework. Then you can compute the autocorrelation function for the square wave that end up to be the triangular wave. This is autocorrelation function. And another wave is a triangular wave. So this is again coming from the box A. So I'm taking, measuring the autocorrelation function of the triangular wave. So triangular wave, as you see, this has a period, of course, for 10 hertz, which is 0.1 second. And this is really consists of many, you can say the sine wave, so close to sine wave. So you expect the output, which is autocorrelation function here, is again the cosine wave. Or you can just generally say the harmonic function again. Okay? So that's what you see here. And the random noise and all that I'll do later, because I have to change the cable, hook up to the random noise source. But I want to finish the cross correlation function and probability density function for 3 waves: pure sine wave, triangular wave, and the square wave. Then we're going to proceed for random noise. So let's look at the probability density functions. So here is, well, now the calibration in progress. So once in a while, getting into the automatic mode to calibrate the system. So you have to wait for a few seconds, and I'll continue on this. But I was going to show you the probability density function of a sine wave and all others. And we have to wait. So maybe...
It's done.
Oh, now it's done. Okay, so I'm going to punch the histogram. So it said PFD1. I'm going to punch this. This is a probability density function, and I'm going to restart. So this is I'll back to sine function. This is harmonic function. This is again signature from this box. And as you see here, let me look at the window. Its hanging window is okay. As it averaging, it's just coming down. So you expect the probability density function. I'm going to push this button. Probability density function. Okay. You expect straight up. This is minus the peak value. This is a plus peak value. And if I just put this is gonna be really the center, or this is a mean value. You can say that. So this is what we learned about the probability density function of the sine wave. Okay, so I'm going to show you next is the cumulative distribution function, which is here. So which is nothing but the progressive addition of the area under the probability density function. So start from the 0 all the way to 1. So if you look at here, this point is a 1. Okay, this is a cumulative distribution function, and this is what we learn in the class for the sine wave. Let's look at on the square wave. So square wave, I push this button here, and I'm going to start. Let's see what the square wave does it. Square wave and PDF function. It looks very interesting. This is two peaks, right at here and right at there. Okay, cumulative distribution function should be is a 1. So because of the square in nature, it just goes almost to 0, goes up and down there, straight down there, and it goes up again, and total area under the curve is 1. So this is where that one peak position, this is the location where another peak position. Back to here, this is a probability density function for rectangular wave. Another wave we're going to display is the triangular wave. So this is a probability density function for triangular wave. As you see, this is really changing. Top is changing. What does it do here is taking the average. Okay, so when you take keep averaging, then it smooths out to minimize the random errors and all that. So that's what it does now. So this is really converging to almost flat. So this is a probability density function of triangular wave, which is somewhat similar to the sine wave, but there is no dip. For the sine wave, there is a dip here, but there is no dip. So cumulative distribution function here is straight up. Because of the triangular in nature, this is area under it of probability density function is a 1. So CDF right here, this is area under, which is a 1. Okay, this is straight up, and that's triangular. The wave for the triangular, the wave forms. Okay, next I'm going to show you cross-correlation function. And cross-correlation function, I switch the box A back to the harmonic function, and this the box B signature still I have the sine wave. So when I take a cross correlation, measure the cross correlation function using A signature and B signature, which is really same as taking the autocorrelation function. Okay. So another thing you can manipulate is box A, I put sine. Box B, I'm going to switch to a triangular pulse, okay? Then I'm going to take a correlation function of these two functions. So let's see what does it do. If I show you the combined signature, I'm going to change knob to A plus B, and this is a combination of sine and the triangular wave. But because this B is flashing, it has a dynamic range, the phasing is random and superimposed on the box A signature. That's what it generates this particular wave. So I'm going to show you cross cross correlation of this to this, which means E, so which is a mean of the xt multiplied by yt plus tau, okay, for this triangular signature. So I'm going back to here, the digital signal analyzer. It said cross correlation, and the channel 1 and 2 are the active, and measurement is cross correlation. Then I'm going to start to take a measurement. So it's keep averaging. It keep averaging. I don't know what's going on here. It's all after averaging is almost flat here. This is somewhat interesting. I expect this becomes like the cosine wave. Let's take a look at it again here. This is O2, 2, O2, 1. This is a cross correlation. As it averages, it just goes almost flat, but you see still the wave in there. But still, well, another way to look at it is after we mix it together. This is a mixing of sine function with the triangular function, and this is an A plus B combination. So I'm going to take the autocorrelation of the mixed function, which happen to be should be the same thing, or at least close. So if you do that, so I have to have activate the channel B, which is channel B here, channel B. Then I have to take this guy as auto. Okay, but channel active is channel B. So take again measurement once. So keep wiggles, because this has the dynamic range. Phasing is random, so it's back to, I expect it's back to the cosine type of the function. Of course, this amplitude is automatically rescale. I'm going to try once again to use a two signal. Okay, this is a X signal, this is, let's say, Y signal. So this goes into, A signal goes into channel 1, B signal goes into channel B, and I'm going to say cross correlation function, and channel 1 and 2 activate. So keep averaging. This time seems to be working fine. I'm going to auto range. I'm going to auto range scale. X is auto and Y is auto. So now I just reset the scale to maximize, to show in the box. So this is a Y auto scale. This is X auto scale. Before it was small, but range was big. So now automatically shrink down the scale. Then as you see here, this is a cross correlation of sine and triangular wave. So we expect such a cosine. You can really compute all this. Okay, maybe another interesting thing may be, how about the cross correlation of sine to the square wave? So here, I'm going to back here, cross correlation, and channel 1 and channel 2 is active, cross correlation there, and I'm going to restart. And it's keep averaging right now. Okay, and if I just put it here, this is a mixing of the sine and square wave. So this is really discontinuous wave. because this is a fixed, and add the rectangular wave. Rectangular wave is discontinued wave, and it has a discontinued function. So that's why as you look at the cross correlation function, it keeps changing. Okay, that's what's happening. So over here. Okay, so we'll stop right here. Then I'll rehook up the wires into the different locations. So we'll come back in a minute and show you the random. We came back after lunch, so we'll do the second half of the first lab. We rearranged the instruments a little bit to do the better videotaping. And we have an oscilloscope right at the top of the DSA. Looks pretty good. So here, this DSA has a random noise generator. So we have all different source. So one of the available source is random noise. So we take the random noise from here and hook up to right at the B here, and we disconnected the box B. Okay, so now random noise is coming right here, and this controls. If I put this here, this is second signal is really same as the first one. If I put this in the B, then that's the random noise. Okay, and if I put this is the case that the random noise is superimposed right on the harmonic function, the sine, and that's what happened here. So I reset the lower signature as random noise. So for the random noise here, the random noise, as I just set everything. So here, if I push this button here, this is a histogram. So if I push that button, it shows PDF2 and CDF2. PDF, probability density function, and CDF2 is a cumulative distribution function. And if I push that, this button here, so I activate channel 2. Channel 2 means it's a random noise. And as I push the restart, and it will take the data, then keep averaging. I just said the average exponentially, which means just to keep averaging to eliminate the error in the system. So as you see here, this curve is getting smoother. As you see, this is really a normal distribution. So that's why we call this random noise as a Gaussian random noise, because its probability density function is a Gaussian. Gaussian distribution sometimes called as a normal distribution. Okay, so that's one thing. We are going to introduce this noise into here. Okay, so I'm going to turn this knob to A plus B and display. Then it's going to be output. Output goes into channel 2, which is lower. So I'm going to take take this signature and generate the probability density function. So I'm going to take data here, and as you see here, you start averaging it. So now this is sine plus random noise, and random noise content I can say is high. So it's not fully normal because random noise imposed on the sine function there, so it is a little bit flat top. Okay, so if I reduce the noise amplitude, then let's see what's happening here. So I'm gonna call the source and source level here. Right now, I set as a 2 volt, the peak to peak. Peak to peak means, well, this is from the positive peak to negative peak. And I'm going to reset this voltage as maybe 1 volt, okay? And restart. So now the random noise amplitude is much lower. So if I turn this back here, this is B. This is pure random noise. Before it was a double, now it's a half because I reset to 1 volt peak to peak. So now this is imposed. Add random noise into the sine, so you see a little less random noise. So I'm going to just restart. Then you see that it's really the sine goes up and down. Now it's a combination of noise level plus sine, but noise level is much smaller. Then you see this valley right down at the middle. Of course, if I increase the random noise, let's say the 4 volt peak to peak. So source level, I'm going to change it to 4 volt, then restart. This is, as you see here, when it's superimposed, it's really, you don't really see well-defined sine because noise contamination in the sine wave is quite high. Because this is really 2 volt peak to peak, but now this is really random noise is a 4 volt peak to peak, so it's random noise controls. So you see that you don't see the valley at the middle, which is affected by the sine function. Is mostly random, so it's close to the Gaussian. The probability density function here, as you see. Okay. Cut through autocorrelation function and cross-correlation function of random noise, well, and the sine wave. We went through the sine wave about 20-30 minutes ago. And I'll mix the sine with the random, so we'll take a look at the autocorrelations and so on. Okay, again, this is a sine wave, this is random noise. So if I take the autocorrelation function, I just did it, this is autocorrelation function. Well, we can reset. I activate the channel, the box, so we'll go down on Monday and we'll do this further. Okay? Alright, so only 5 out of 9 students. I really wish they come in on Monday that they do this further. Okay, so Monday will come in as scheduled. After 10 minutes, as I explain what we're going to do, I'll distribute the sheet, then we'll go down.